Today we're doing Chapter 16, Discrete and Continuous Random Variables. A discrete random variable x has a countable, finite number of possible outcomes. The outcomes can be listed. Let's look at example 1. Let x represent the number of girls in a family of 3 children. Create a probability model for x. So here we can list all our outcomes. You could have 0 girls, which would be boy, boy, boy. You could have 1 girl, which could go with in the order girl, boy, 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 girl, boy, or boy, boy, girl. You could have 2 girls, which could be the order girl, girl, boy, girl, boy, girl, or boy, girl, girl. And then the last we could have 3 girls. So our total here is 1, 2, 3, 4, 5, 6, 7, 8. So to fill out our probability model for x, the probability of having 0 girls would be 1/8 because there's only one combination out of 8. The probability of having 1 girl, so 1 girl would be 1, 2, 3, would be 3/8. The probability of having 2 girls, 1, 2, 3, would also be 3/8. And the probability of having 3 girls is 1/8. And what you notice about our probability model, if we added all those probabilities together, we would get 1, which you should. Let's look at example 2. You draw a card from a standard deck of cards. If you draw the ace of hearts, you win $100. For any other ace, you win 10. And for any other heart, you win 5. If you draw anything else, you lose. The game costs $5 to play. Do you want to play? Let y represent the winnings. Create a probability distribution for the expected winnings. So we have y here. For the expected winnings, you could win nothing, or $5, $10, or $100. And if we win $100, that's the ace of hearts. That's just 1 out of 52 because there's 52 cards in the deck. To win $10, it's any other ace, and that would be 3 out of 52 because you have the ace of clubs, spades, and diamonds. To win $5, it would be any other heart. We have the ace of hearts up here. There's 13 cards per for each heart, diamond, club, spades. So since there's 1 here, it would be 12 out of 52. And then the remaining cards that we have would be 36 out of 52. And we're going to come back to these 2 examples in our examples to come. The mean of a discrete random variable. The mean of a discrete random variable x is its weighted average. Each value of x is weighted by its probability. To find the mean of x, multiply the value of x by its probability, then add the products. So for example, the expected value of x would be the mean of x, so it would be x1 times the probability of that, all the way until you have them all added together. The mean of a random variable x is also called the expected value of x, or E of x. Example 3. Calculate the mean number of girls in a family of 3. So this would mean I'm finding the mean of x. So when I have 0 girls, I would multiply that by the probability of 1/8. Plus, when I have 1 girl, that would be multiplied by its probability of 3/8. So we're referring back to that example 1. When I have 2 girls, that would be multiplied by the probability of 3/8. And when I have 3 girls, that would be multiplied by the probability of 1/8 because that was its probability. We take these, add them together, so we would have 3/8 plus 6/8 plus 3/8, which would give me 12/8. And my expected value would be 1.5 girls. Let's look at example 4. Calculate the expected win-ins in the ace heart game. So my expected win-ins, referring back to example 2, would be 0 times 36 out of 52 plus 5 times 12 out of 52 plus 10 times 3 out of 52 plus 100 times 1 out of 52, which would be 190 out of 52, which would be about $3.65. Based on this result, that game costs $5 each time you play. Would you play? So that's a question only you can answer. But if you're only expected to win $3.65, would you want to pay $5 with expected to just win that amount? Let's look at the variance of a discrete random variable. If x is a discrete random variable with mean x, then its variance is you take the x value minus the mean, square it, and times it by the probability, and you add each one of those for each individual result. To find the standard deviation, we just square root the variance. So let's calculate the standard deviation for the expected win-ins in the ace heart game. So in order to get the standard deviation, we first need to have the variance. So I want the variance of y. So it would be 0 minus 3.65 squared times 36 out of 52 plus 5 minus 3.65 squared times 12 out of 52 plus 10 minus 3.65 squared times 3 out of 52 and plus 100 minus 3.65 all squared times 1 out of 52. This would give us about $190 and 190.496. So to find the standard deviation of y, we would have to square root 190.496. When I square root that, I get about 13.802. So the standard deviation is about $13.80. Rules for means and variances. If x is a random variable and a and b are fixed numbers, then the mean of a plus bx equals a plus the b times the mean of x. And the variance, it would be b squared times the variance, and the standard deviation would be b times the standard deviation. So let's look at example 6. Back to the ace heart card game. If the win-in amounts were all doubled, what would the mean and standard deviation of your expected net win-ins? So this includes the cost of playing. So in order to get this, it would be mu -5, because that's the cost of playing, plus 2y. So my mean would be -5 times 2 plus 2 times mean of y, which would be -5 plus 2 times 3.65, which would be $2.30. My standard deviation of -5 plus 2y would be 2 times my standard deviation of y, which would equal 2 times 13.8, which equals 2760. So the only thing that affects this is that doubling, because that changes what the shape of the curve is. However, that -5 just moves it left and right. So it doesn't affect that standard deviation or variance. More rules for means and variances. If x and y are random variables, then the mean of x plus y equals the mean of x plus the mean of y. The mean of x minus y equals the mean of x minus the mean of y. If x and y are independent random variables, then the variance of x plus y is the variance of x plus the variance of y. The standard deviation of x plus y is those variances taking the square root of it. Now, when they're subtracted, you never subtract variances and standard deviation. You always add them, okay? So back to the card game one more time. Imagine playing the original game twice. What are the mean and standard deviation of your net win-ins? So our mean would be -10, because that's how much it was to play, plus y1 plus y2, which would be -10 plus mu1 plus mu2, which equals -10 plus 3.65 plus 3.65, which would be -$2.70. So you'd be losing money if you played twice. And my standard deviation would be -10 plus y1 plus y2, the 2 times I played, which would be the square root of my variance of y1 plus my variance of y2 squared. So this would be the square root of 190.496 plus 190.496, which equals $19.52. A continuous random variable can have any value in a given interval. We cannot list all the possible outcomes of x. The probability distribution of a continuous random variable is shown by a density curve. The probability that x is between two values is the area under the curve between the two values. So for example, I have my density curve here, the normal curve, and this would be x. This is my probability. These would be my two values, and this is the probability under the curve between the two values. So let's look at this example. Suppose a used car dealer runs autos through a two-stage process to get them ready to sell. The mechanical checkup costs $50 per hour and takes an average of 90 minutes, with the standard deviation of 15 minutes. The appearance, prep, wash, polish, etc. costs $6 an hour and takes an average of 60 minutes, with a standard deviation of 5 minutes. What are the mean and standard deviation of the total time spent preparing a car? Note, we cannot find the standard deviation if we do not believe the two phases of the process are independent, an important assumption to check. So we're going to let M equal the mechanical time in minutes, A be the appearance time in minutes, and T be the total time. So our total time would be M plus A. So the expected value of our total time would be the expected value of M plus the expected value of A. The expected value of M, is 90, And the expected value for A is 60. So our expected value for time would be 150 minutes. And in order to find our standard deviation of this, we first need to find our variance of t. Our variance of t would be the variance of m plus the variance of a. The variance of m would be 15 squared plus the variance of a, which would be 5 squared, which equals 250. So my standard deviation of t would be the square root of 250, because in order to get the standard deviation, you would square root the variance, and that would be 15.8 minutes. So we expect the total preparation time to take an average of 150 minutes with a standard deviation of 15.8 minutes. What is the probability that it will take longer to do the appearance prep than the mechanical checkup? No, we cannot answer this question unless we believe each phase of the process can be described by a normal model. So we're assuming that. So we need to introduce another variable, the difference in times. So D is going to be the difference in times. And it's going to be M minus A. And the probability that it will take longer to do the appearance prep than the mechanical prep would be M minus A, and that would be when it is less than 0, okay? Our expected value of D would be 90 minus 60, which equals 30. And our standard deviation of D would be our standard deviation of M minus A, which would be the variance of M, which is 15 squared, plus the variance of A, which is 5 squared, which equals 15.8 minutes. So the difference in prep time varies according to the normal model, with mean 30 minutes and standard deviation 15.8. So we're going to use this to find the probability that it will take longer to do the appearance prep than the mechanical checkup. So we're going to use the normal model. So we're always going to draw a picture of this. You'd have your normal curve with our mean of 30. And here our standard deviation was about 15.8. So I'm just going to draw in my 3 standard deviations so that when I'm drawing my picture, I can sort of guess where everything would be. Okay, so what we need to do is we need to standardize our value. If we're going to go ahead and draw in where the difference would be, that would be at 0, okay? And it would be everything before 0 because it would be negative. So here I have 30. I know this is about 15.8, and then this is about another 15.8. So that would be 31.6. So 0 is right about here. So you can just estimate that. We're looking for that area. So this would be 0. Okay, so you want to label that. In order to actually find this, we need to standardize 0 if we were going to use our table. And you also need to be able to find that standardized value. So to find Z, it would be your value minus your mean, which is 30, all over your standard deviation, which is 15.8. So if I was using the standard normal model, this would be negative 1.899. Now you can go to your table, which I can show you in class, for your normal model, and you would find negative 1.899, and you would be able to find the probability that came with that. Or you can use your calculator and use norm CDF, which is under distribution, which is the second in Barsky. We're going from negative infinity, so negative infinity up to 0. So you'd put negative 1E99 in your calculator. The E is the double E button above the 7, which you have to press second for, up to 0. And since it's the normal model, or not up to 0, excuse me, up to our standardized score of negative 1.899. And you will get about 0.0288. So my probability, the area under that curve right here, that area is 0.0288. So we would expect the appearance prep to take more time than the mechanical checkup, about 2.88% of the time. What are the mean and standard deviation of the total expense to prepare the car? So we have M being the mechanical time, A being the appearance time, and T being the total expenses. So and they want this in hours. Remember in the example, it was given it to us in minutes. So we need to change it in hours. So the expected mechanical time is 1.5 hours. The standard deviation of mechanical time is 0.25 hours. The expected appearance time is 1 hour. And the expected, or the standard deviation of appearance is 1/12 of an hour, which is about 0.0833. So if I want to find the total, my total would be 50M plus 6A, because I have to multiply by how much it costs. So the expected total would be 50 times my expected M, which would be 50 times 1.5, plus 6 times my expected A, which would be 1, and that would be $81. So my expected total expense is $81. The standard deviation would first, I would have to find my variance of my total expenses, which would be 50 squared, because that's how much it would cost, times the standard deviation of the mechanical time, which would be 0.25, and you would square that, plus 6, the cost, times 1/12 squared. And that's about 156.5. To find my standard deviation, I would just have to square root that, and that would be about $12.51. So we would expect the total preparation expense to average $81. So this should be $81 with a standard deviation of $12.51. So you always want to answer in a sentence. That's why I have those sentence stems there. What are the mean and standard deviation of the difference in expenses of preparing a car? Since we believe the two phases of the process are independent, the variances add. Remember that. So D is going to be the difference in expenses. So D would be 50M minus 6A. So my expected D would be 50 times 1.5 minus 6 times 1, which would be $69. And my standard deviation of D would be the square root, and you can just go right into it. You don't have to find the variance every time. You can just go and do the work. Would be 50 squared times 0.5, or 25 squared, plus 6 squared times 1/12 squared. And again, we would get 12.51. That doesn't change. So we expect the difference in preparation expenses to average $69 with a standard deviation of $12.51.